So as we've gone through these pages, you might have asked yourself, well, how do you know when to use the mean with standard deviation, or when do you use the median with interquartile range? Those are your choices. So I think it depends on the data set you're given. Our next example shows that the shape of the distribution and the presence of outliers helps us answer the question of which one to use. Let's see. Here are two summaries of the same set of homework scores earned by a student, a box plot and a hat plot. Notice that the distribution of scores has an outlier. This student has mostly high homework scores, but with one score of 0, which is fine. Yeah, you miss one homework, you're probably okay. So the 5-number summary, the lowest score was 0 because they just didn't do that homework, they missed it for whatever reason. But quartile 1 ends at 82. That's a B. That's pretty good. So if you take all your scores from highest to lowest and you divide it in 4 pieces, right? The lowest quarter of your data, the highest of that is 82. That's pretty good. That means 3/4 of your data is higher than 82. That's really good, right? Don't feel bad. Quartile 2 ends at 84.5, so not very far away from quartile 1 at all. Quartile 3 ends at 89, and the high is 100. That's awesome. So this person's doing great. They just missed one homework. Big deal. Median is 84.5. The interquartile range is 7. The mean is 81.8 with a standard deviation of 17.6. So these are all things, if you're wondering, oh my gosh, where did they get those numbers? What the hell? These are things that StatCrunch would do for you, or some other computer program. In real life, people don't do these calculations on their own. They just type all the data values into some program, and the program does it for them. Yeah, don't worry too much about it. Anyway, so what do we have now? So measuring these, depending if you use mean and standard deviation versus median and interquartile range, your typical interval is going to be different. So the typical interval of scores based on the first and third quartiles, so if you're using median and quartiles, is between 82 and 89. So a 7-unit range between 82 and 89. Okay. But on the other hand, if you use mean and standard deviation, the typical interval is between 64.2 and 99.4. So, and then the calculation they said was 81.8, 17.6, subtract them, you get 64. So that was, remember on the previous page we said mean plus standard deviation will give you the highest value, and then mean minus standard deviation. Anyway, that's where they got these two. So which is the better summary of the student's performance on homework? Well, the typical interval based on the mean and standard deviation is not a good summary of the student's homework scores, because it's just based on the quartiles. Like we said before, the 3/4 of this student's homework were better than 82. But if you use the mean and standard deviation, you'd see that their range of values here, let's see, I want to make sure we're talking about the same thing, is between 64.2 and 99.4. So that kind of makes it seem like this student has a wide range of homework scores, when really, like we said, 3/4 of these scores were above 80, was it 84, 82? So it feels like this is a better indication of it. I guess the typical interval based on the mean and standard deviation is not that great of a summary for the student's homework scores. Here we see that the outlier decreases the mean, so that the mean is too low to be representative of the student's typical performance. We also see that the outlier increases the standard deviation, which gives the impression of a wide variety of homework scores. This makes sense because the standard deviation measures the average deviation of the data from the mean, and 0, a score of 0, is very far from the mean of 81. So a point that has a large deviation, yeah, like that homework score of 0, kind of brought everything down. In this example, a single score is responsible for giving the impression that the student's typical homework scores are lower than they really are. The typical interval based on the first and third quartiles gives a better summary of the student's performance on homework because the outlier does not affect the quartile marks. So that's, I guess, the answer is if there are outliers. I mean, I guess, like this one has outliers that are way off. Most of the data values they're all passing scores except one. So this student's passing this class, but they only had one homework score that wasn't passing. If you have an outlier that's way far away from the mean, or median, whatever, you're going to want to use median and quartiles instead of mean and standard deviation. So now we'll look at another example with skewed distributions, where the majority of the values are either really low or really high. So in the example below, we'll look at how skew in a distribution affects the standard deviation. The following histogram shows the personal income of a large sample of individuals drawn from U.S. Census data in the year 2000. Notice that it's strongly skewed to the right, because most of the data is on the left. This type of skew is often present with variables involving money, such as income, housing costs, etc. So here in this data set, the x values range from 0 to, 240,000. The mean is 24,000. The standard deviation is 27,500. On the other hand, though, if you use median as your measure of center, the median is 16,900. The interquartile range is 28,000. So let's explore which one would be better depending on this skewed sample set. The typical interval based on the mean and standard deviation is not a great summary of the distribution of incomes. The small number of people with higher incomes increases the mean. I think we saw an example on a previous page a while back that talked about this too. The mean is too high to represent the large number of people making less than 20,000 a year. The small number of people with higher incomes also increase the standard deviation. So even though there aren't outliers, it's not like, I guess I wouldn't call them outliers because it's not like there's a big gap, there's no values in this area, there's only large ones and small ones, you know. It kind of slowly tapers down. So I wouldn't call those outliers necessarily because they're not, yeah, there are data values in every one of these little areas here. But it's definitely skewed in this case. So the mean, yeah, it's too high, the standard deviation is too high. Notice also that the mean plus or minus the standard deviation gives an awkward range of typical values. The left endpoint is negative 3,500. What the hell? How can you even make, well, you owe money, I guess. I was going to say, how can you make 3,500 as your income? And then there are no negative values in this data set, so it's kind of weird to say that a typical range of values is a negative number as the lowest value. This is another reason why it's better to use the interquartile range when measuring the spread of skewed data. So let's take a look at the same histogram, except this time we'll overlay a box plot. So it looks like here, where we got it. Here are the middle quartiles, quartile 2 and quartile 3. We see that the median represents the typical income of people in the sample better than the mean. The small number of people with higher incomes does not impact the median or the other quartile marks. So the first and third quartile marks give an interval of incomes that more accurately represents typical incomes in the sample. Notice also that the interval is always within the overall range of data, so we will never have the problem that we encountered earlier with the standard deviation. Okay, so we see that the median represents the typical income of people in the sample better than the mean. The small number of people with higher incomes does not impact the median or the other quartile marks, so the first and third quartile marks give an interval of incomes that more accurately represents typical incomes in the sample. Notice also that this interval is always within the overall range of the data. So we will never have the problem that we encountered earlier with the standard deviation. Yeah, earlier we said the standard deviation gave us a negative value as part of your typical range of values, but no one can make a negative number of money. That doesn't make sense. Because we're talking about income. That's only what you're given, not what you have to pay. In a skewed distribution, the upper half and the lower half of the data have a different amount of spread. So no single number, such as the standard deviation, could describe the spread very well. We get a better understanding of how the values are distributed if we use the quartiles and the two extreme values in the 5-number summary. Here are general guidelines for choosing numerical summaries. So we will use the mean and the standard deviation as measurements of center and spread only for distributions that are reasonably symmetric with a central peak. When outliers are present, the mean and standard deviation are not a good choice. So you probably want to see a bell-shaped curve. I think we'll talk more about that later. But if you see, here's your data spread and it kind of goes like that. It's pretty symmetric. I mean, basically that. It doesn't have to be perfect. But something like that with not a lot of outliers, then you're going to use mean. But if you see some skewed data, like we just saw in the above example, or outliers, then you're going to want to use the median. So it's kind of like if you have nice data, quote unquote, nice data that behaves well, it's not skewed to left or right, it doesn't have a lot of outliers, then you want to use the mean. But if it's kind of misbehaving, it's skewed to the left, it's skewed to the right, it's not a nice bell-shaped curve, then you're going to want to use the median and quartiles. So we use the 5-number summary which gives the median, interquartile range, and range for all other cases. Both of these examples also highlight another important principle. You always plot the data. Just because if you just see a list of data values as numbers, it's hard to tell how the data looks. Is it bell-shaped? Is it skewed to the left, skewed to the right? I guess you can see outliers in the data, but that way you can decide which measure of center to use. We need to use a graph to determine the shape of the distribution. By looking at the shape, we can determine which measure of center and spread best describe the data.